We are live.
So were we expecting anybody else, lad, or is it just you and Mario?
As far as I know,
Okay.
with Horace and Carlos, I don't know exactly how they're doing. This was a little unexpected. You have to do an installer and stuff, and I think they're on Windows. So,
Okay. All right. Well, we'll run with it. Like I said, just a little test run, see if we like it or not. So what we're going to talk about today is the blockchain code that's been released and is up on GitHub. Uses pretty typical approach you'd find in Java, where we're opening up sockets to communicate between different instances, and we're serializing Java objects to communicate. So what I'm going to do is kind of show that very typical Java code really fast, not spend a lot of time on that, and then we'll look at how that gets changed over to using protocol buffers and GRPC. And then we can talk about that in more depth and see what you guys think of these libraries from Google. Sound good?
yep.
Okay, well, let me share my screen here. Okay, so you guys should be seeing my screen now. And what I've got up right now, this is the daemon for the blockchain. So this is responsible for the full node on the blockchain, which means that it needs to act as a server where various other clients can connect to it, including other nodes. And then it also needs to act as a client as well and connect to other nodes. So it's peer-to-peer. So real quick, running through the code, some of the things you'll see here are, here we're opening up sockets to each of the peers that we want to connect to. And what's important here is that we get a socket, and then we allocate what I call a network thread to that socket. So that means that for every connection to a peer, I'm allocating a thread to it. This way, we can communicate with those individual sockets as separate threads. Now, what that means, this is using blocking I/O, which means that the thread will block whenever there's nothing to do on the network side. But because it's multi-threaded, we'll be able to run multiple threads at the same time, so it won't appear blocking. Now, this is not considered to be the most scalable way to do that, because as you add more and more threads, the overhead of handling connections gets higher and higher. There's more sophisticated ways of doing this in Java, and it's generally referred to as NIO, which is the new IO that allows you to do non-blocking. And that gets much more complicated in code, and I didn't write all that. That was going to be the next step, but I stumbled upon Google's protocol buffers and GRPC, and that looked like a better way to go. So that's what I did. So again, here we are allocating a thread when we are connecting to a peer. And then here is our server socket, right? So we open that port up, and then we wait for connections. And so here's our while loop waiting for connections. Whenever we get one, we accept it, and then again we allocate a network thread. So it doesn't matter if we're connecting to people or people are connecting to us. We always essentially end up in the same place. We allocate a thread and we tie it to their socket. And so now let's look at what that networking code actually looks like. Here is our network thread, and what this does is it has an infinite loop that is waiting to read data from the socket. Again, this is a very traditional way of doing that. And then we've got this crazy long if, because what we are really doing here is we're reading an object, which is an object stream in Java. So that means we're letting Java handle all of the serialization and everything else that happens on the wire. And that sort of also means that doing this with a non-Java is very difficult, because you have to end up writing the Java serialization and deserialization routines in your other language, which is obviously not good. But this was very easy to do. So we read the object, and that gets us an object, and then we have to figure out what kind of object. And so the way I implemented our network protocol was that I created a bunch of different types of message objects. And so that's, let me go over and show you one of those. So this is an abstract message. So all messages extend abstract message, and they have some basic properties to them. We know what network they're associated with. Network parlance can also mean blockchain, what version of the chain that we're running. And then we also keep up with some basic other data. Now, for any particular message, like for instance, if you wanted to send a block from one peer to another, you would send a block message. And here's what a block message looks like. It is basically a message that contains a block, right? Very, very straightforward. But so what we're doing here is all the communication between the daemon and other daemons and clients is all wrapped up in message objects, and Java takes care of everything behind the scenes, and we just have to know what a message object is and make our own custom messages for any kind of communication we want to do. So when we go back to here, this big if, all it's really doing is finding out what kind of message came over, and then we cast it. So for example, if it was a block message, we cast it over to a block message, and then we send it to a handler to deal with that. So similar thing happens over and over and over again. So this networking code looks very straightforward. So essentially the two hosts, they communicate in messages, and then we allocate some function to deal with that message. So you can see there's a number of different message types here, everything from dealing with blocks to transactions to what have you. A really straightforward one that I do is a welcome message. And the idea is when hosts first get connected to each other, they exchange a welcome. And the welcome looks like this. It basically says, hey, this is what my time is. And for my chain, this is what the current difficulty, reward, and then here's the latest block that's on my chain. And that's useful because if my latest block is, newer than yours, then I might have a longer chain, and we need to start talking about how to synchronize our chains. So it's just a good sort of way to get the two hosts to know where they stand and start out working that out. Any questions there? I know I'm sort of breezing over this right now. But assuming there's no questions, let's just look at this, an example here of handling a welcome message. So here's that if, where we get a welcome message, and then we go to handling the welcome message. So if we actually jump up to that particular function, here we are. So we get the welcome message, and we do a couple of things and say, okay, hey, it looks like someone just claimed that they've got a longer chain than we do. So if that's true, then we're missing some blocks. So we basically send a message over to them asking for their blocks, and so on and so forth. And you can imagine all the different sort of ins and outs you could do with network communication. So now if we look on the client side, this is something that would connect to the daemon, and it also has to talk networking code. So let's take a look at that, and you'll see it's again very straightforward. Here we are opening up the socket connection, and then we're getting our object streams again, and here's that same kind of infinite loop that's reading an object, and look, another big set of ifs of which message to do, and then we're going to do something about it, right? So as you can see, all this Java code for dealing with the networking side is very straightforward, but it's not scalable because we have to allocate a thread for every client. Plus, it's only going to support Java, not other languages very easily. And also, some of the issues are if these message change, like, we want to add fields or something like that to the messages, we can get into some versioning issues where different messages on different machines have different versions and how to communicate that. So I solved that by passing over a version parameter, but it's a real issue to deal with. Now, you're probably thinking, well, gosh, wouldn't this be easier if we just switched it over to doing like REST and JSON? So now if we did that, we wouldn't have to worry about having a Java specific serialization format because we'd be using JSON. And we wouldn't have to worry about all this socket code and allocating threads. We could just run web servers and do HTTP. But as you can imagine, that actually increases the overhead even further than doing this. So all you really get is cross-platform capability. You don't actually get a performance increase, you get a performance decrease. Because serializing to JSON is going to be slower than the binary serialization method that we're currently using. And for anybody who's done any serialization work with JSON and Java, you know that there's a bunch of other things that you have to deal with that can sometimes start putting a lot of things in your code that you don't like. And then, of course, at the end of the day, doing it on top of HTTP means you have to have web servers, and HTTP is a clear text protocol that has its own scalability challenges. So where do we go from here? Well, we look at protocol buffers. So if you see my screen now, I've sort of brought up the website for protocol buffers. I don't know if you guys have seen this before, but this is a project that Google started. And essentially what they've done is they've come up with an intermediate language, just like you would have JSON being an intermediate language. In this case, they have one that's a binary-based protocol that works with a variety of platforms. You can see they name several here: C++, C#, Go, Java, Python. There's certainly JavaScript, Node, and a whole bunch of other ones as well. And so what does this look like? They've come up with a little language where you can describe an object as a message, and you can put in some information in this very simple language to describe it. And, they've got your complete language guide here of, explaining how to do it, specifying the field types, so on and so forth. But that's not all that they've done. They've taken this same language, which was called Proto, designed for the protocol buffers, and they've actually also created this other library called GRPC. And GRPC uses the same protocol language, but it adds in the ability to describe endpoints. And you can see in their diagram here essentially what they're talking about. You can now have different servers and stubs all talking to each other regardless of language, and they're using protocol buffers in the middle to do that. But it's not just that they're doing binary data from one side to the other. The other thing that they're doing is they're using HTTP 2, which is a binary version of HTTP, which is much faster, and it also supports multiplexing. So this is sort of the new modern way to do things that is going to overtake JSON and REST as time goes on, because it's performed so much better. So let me stop there for a second and see if anybody has any questions before I start showing you how I actually went about changing from that Java code over to using the new protocol buffers in gRPC.
So what's the ramifications? I mean, obviously, gRPC is, the latest and greatest thing. but it was built to kind of solve a particular problem. And can you maybe outline that a little more for me? Because like, it seems like it's good, but I don't have a reference point, if that makes any sense, Matt.
Well, it's high performance and scalability, right? So,
Well, I know that, but it's like there's a current limitation on some socket that, you know, is because of X, but because GRPC is doing something, do you feel like that's what I'm trying to wrap my head around, other than the fact that, you know, I mean, I know you're a smart guy, but, you know, I'm trying to understand conceptually why
well,
GRPC.
they've solved problems in a way that makes it easier for developers to do this. So one thing is you need a serialization format if you're going to go from one platform to another. And so using the built-in Java one works really well if you don't want to write a bunch of code and the two platforms that need to communicate are Java. But if you want to go cross-platform, suddenly you need something else. And JSON is typically what is used, but you know, there ends up being a decent amount of code that has to be written just to exchange JSON, because JSON is not really native to Java. It's more native to JavaScript, and they sort of made it work on Java and other platforms. So what they did with protocol buffers was they designed something from the ground up that was meant to be highly efficient and work with multiple languages. And I'll show you when we get to the Java side why that is actually but the big difference here is that it's binary. So it's very, very compact and very fast to serialize and deserialize compared to JSON. That's really important. And then as you get into the RPC side, you have the advantage that HTTP2 has been designed from the ground up to be high performance. And so you get that sort of for free by working with gRPC, as opposed to having to write your own HTTP2 interactions.
Mm. Okay, that helps. Just because for me, I didn't have a reference point, so it helps for me to get grounded.
Right.
I don't know if anyone else has any questions, or it seems like everyone's shy.
I'll ask a question. The HTTP2, it comes, you say you use gRPC, you get HTTP kind of for free. So how does that work?
Lad, can you speak up a bit? You're a little muffled.
Yeah.
Sorry. I don't know if it's a mic thing or.
Yeah, no, I think I heard your question, Lad. You were asking about HTTP2 getting it for free. Go on.
Yeah, my question is like, so how does that work? I mean, in HTTP1, you know, we're used to having web servers, as you say. So we avoid the need to have a web server, or we have a different web server that's more lightweight and more high performance. How does that work with gRPC?
Right. So you're spot on. So you have to have something that does all the protocol work for you. And so if we were doing, you know, let's say JSON, REST in Java or what have you, we would need a web server. We could, you know, run a full-blown web server if we wanted. We could embed Jetty. There's a whole variety of small embedded web servers that are designed exactly for the task of doing kind of API level work that take care of all that sort of HTTP work for you. And then there's, of course, the HTTP client that's built into Java that allows you to make remote calls via the API. So yeah, all that stuff is there. Now, one of the things I talked about earlier was that the code that I had in Java was using a blocking approach, and that there's the new or better way of doing it, which is NIO, which involves non-blocking. And I could write a whole bunch of Java code to deal with non-blocking, but you end up getting into the weeds pretty far with that. And the folks who have written web servers, they deal with all those issues and, you know, have abstracted it up to the HTTP level, making it really, really easy. So I know this is a long answer to your question, but there's a project out there called Netty, and Netty was designed to be a framework that sits on top of Java NIO, making it easier for you to implement your own servers, including let's say, an HTTP server. And so what gRPC has done is they've essentially built an HTTP2 server and client on top of that. So all the hard work of getting HTTP2 is done for you by gRPC. So you don't have to worry about going and finding a web server and all these other things. It's all sort of built in. And one of the things that's built into it is that it understands HTTP2's multiplexing, and it uses the binary aspect of protocol buffers and the multiplexing aspect of HTTP2 to move the data much more efficiently. So I don't know, did that answer your question?
Yeah, pretty much. I was just Googling it while you were talking. It looks, so I think I get it.
Okay. Anybody else, or should we hop over and see some protocol buffers?
Let's check it out.
All right. So I'm going to share my screen again, and I'm hopping back into the code. And so we looked before at the daemon and client that we had, and you saw all these Java classes describing messages that were written in pure Java code. Now what I'm going to do is I'm going to show you my protocol buffers. So I have this file called tokenservice.proto, and this uses the version 3 of the language, and it's really straightforward, as you can see. So first thing I do is I describe the service, and you can think of a service much like an API in REST. And you know how in REST you have different endpoints that might be associated with your API? Well, this service has different endpoints, and each one is named as an RPC. And the syntax here is really straightforward. Basically, this is the name of my RPC. This is what I expect you to send me as far as data, and this is what I expect to return back to you. So this is a very straightforward call right here. Send me this, I'll send you that. And each of these follow that same straightforward approach. Now these last two are slightly different. These are streams. And in fact, these are actually bidirectional streams. And so what we're doing here is we're saying, okay, if you call this RPC, you're going to send me a stream of transactions, and I'm going to send you a stream of transactions. And this one is the same thing. And so basically a stream just means that, hey, you're going to open it up, and we're just going to keep sending, in this case, this last one, blocks back and forth to each other with no known limit or anything like that. Just if we have them, we'll send them, and we'll let you know when you get a new one, kind of thing. So that's how we've described the endpoints, right here in one place. All right. Now let's actually take one apart here. So let's look at welcome. You may remember from the Java code what welcome was supposed to do. When the two hosts connect to each other, they're going to welcome each other, and part of that welcoming, they're going to exchange some information about the blockchain. So in this case, we're doing a similar thing. The welcome request is the connecting side saying, hey, this is what, this is me, and I'd like to know about you. And welcome response is the response. So these are described here, welcome request, welcome response. So now let's take a look at what a welcome request looks like. So we'll scroll down here, and here's our welcome request. And this is pretty straightforward. We create an enumeration, and the point of this is to tell the remote side what kind of peer we are. And I've got three choices: node, client, and miner. And so a node is going to be the full-blown thing that holds the blockchain and communicates with other nodes. A client might be like a wallet, or you just want to do some really lightweight work. And then, of course, a miner is going to be interested in new transactions so they can create a block. So we define the enum here, and then we actually use it right here. And so the welcome request sends over literally one piece of data, which is what type of peer you are. And then if you recall, when we scroll back up, we get a welcome response. And our welcome response is right here. And this one is a little bit different. This one has repeated, which is essentially a way of saying that this message type here, you're going to get multiple of it. So think of it like in a list or an array of welcome models. And so that's what we're going to send, is essentially a list of welcome models. And what does a welcome model look like? It looks like this. We basically say, okay, first we're going to tell you what network it is using the network model. And you can see the network model here is just an enum. There's two networks, token and test. So this is what network the server is. And then here's my local time as a timestamp, you know, in UTC, whatever it thinks it is, the current difficulty of the blockchain, the current reward of the blockchain, and the latest block. And of course, the latest block is of type block model. And right here is what a block model looks like. Blocks are tied to specific networks. That seems redundant, but sometimes blocks come over that are not associated with welcome, so we still have to know what network they're a part of. Index is essentially, you know, which block it is on the chain. Hash is the hash of the block. The previous hash is the block that it points to. The timestamp of the block. All the transactions. Here, this is repeated. So again, just like what we've seen before, this is going to be like a list of transactions. And what the difficulty of the block was, and the nonce, which is, you know, again, how the proof of work was calculated. So these are all just defining types, and you can see that they can relate to each other and be nested. But it's all right here in this one file. Any questions?
No.
So let's do something real quick, and then we'll look at how it actually gets done. I'm going to turn up a daemon that hosts this RPC get welcome, and then I'm going to connect to it with a client. Using GRPC, we're going to run this RPC and see what we get. So here I'm starting the daemon, and you can see it says running. And now I'm going to do the client. And voila, I got a response. And as you can see, I got 2 welcomes. And here's the various data that you would expect. So there's a couple of interesting things you see here. So if you recall, when we looked over here at what a welcome model looked like, the very first thing that we described in the welcome model is a network. And a network has to be either token or test, right? Because it's an enum. Now, when we look over here, we don't see network anywhere. But in this one, we do. Now, that's one of the first little optimizations that we're seeing. And the reason for that is because protocol buffers knows that this is the 0 value of the enum, which it calls the default. And so it doesn't send over defaults because that would be a waste of space. It only sends over ones that are not that. So that's a small optimization that it made. And we will actually see that in various other places. So remember, that was supposed to be here, and then it also would have been in the block. And so in both cases, you don't see it here. Whereas over here, we see it here, and we see it here, and then again, we see it here, right? So, you know, protocol buffers is being really smart about sending as little data as it can to properly describe the object. So you can see all this worked and everything else. Now, you must be saying, okay, great. I could have sent JSON over HTTP, and it would have been just as straightforward and easy, and I wouldn't have had to do this protocol file and everything else, right? So let's look at what this actually looked like in code form. So here is our client, and essentially what we do is we establish a channel to that remote server. In this case, it was localhost, and then we get a stub. Now, in this case, I've got two different stubs. One's for blocking communication and one's for asynchronous. You wouldn't necessarily use both. You could use one or the other. In my particular case, as I wrote this, I'm using the stub for the RPC call, like the welcome, and I'm using async for the streaming. But nevertheless, here is that call. So these two lines of code are what we saw in the output here. It connected to the stub and said, hey, do the get welcome, and then it printed out the response. So literally that easy. Now, if you recall, what we had to do is we had to send over a welcome request. And so that's right here. Now, this seems like a whole bunch of things, but what's happening here is that it's providing you a builder that lets you build up the object that you send over. So, you know, if we were to break that down into several lines, you know, you basically, you get the builder, and then here is where it sets the peer type, and then it builds it. So
Matt,
yeah.
if you had more than one parameter to set in your builder, would you just chain it together, new builder, set peer type, new builders, just do it over and over again in the same line?
Yes. So we can take a look at that. For example, you know, here, let's see, let me find a good example. So here's one where we're actually creating a block. So this is a utility class that I made. And so here's my Java block object, and I want to transform it into the block model that gets sent over the wire. And so here we're doing block model, new builder, and then here's our various setters, and then it builds it.
Nice. Okay, thanks.
And so I made these transformers so that I can basically take the internal representation of objects and transform them over to the protocol buffer in basically one line. And that separates all of that. Now, you know, this would be another way you could deal with JSON and dealing with all your annotations and other things like that. But this actually turns out to be a little bit nicer than the way you do it with Jackson, for example. So one of the things I want to show you, you may remember in the daemon code how much code there was for dealing with the network. Here is this thing just got in my way. There we go. Here's the daemon. So basically, that's it, right? You know, I say, hey, get me a server and on this port. And that's pretty much it. Now, obviously, it's not just one line. So this is the main method where we say, okay, get me the server and start it and await termination. Now, what happens behind the scenes is that we're actually, we have most of the work done in the token service implementation. So I'll open that up right here. And so this is where it really happens. So here's that get welcome implemented. So we get our welcome request, and then we have a response observer where we can put back the welcome response. And so if you remember, we only get that one piece of information, which was the peer type. So we get that. And then here is our response back, where I basically create a welcome response, and I put in the various information and send it back. Now, this is a little bit more complicated because I'm sending multiple welcomes. So this is a loop. So you can see I'm using the stream here to basically, for each chain that I have on the server, I return one specific welcome model, and this collects them all as a list. But that's how very straightforward this is. So on the server side, you write this, and on the client side, you write this. And all the binary stuff, all the HTTP2 stuff, it's all done. That's pretty cool.
I can imagine that the performance increase is pretty significant. Do you have any idea? Have you had any? Have you looked at it at all as far as how significant it seems to be?
I haven't done any testing myself, other than just observed it being faster. But there are folks who have done performance testing, and it is obviously substantial.
And it seems like there's also considerably less server config and setup.
Yeah, so this is not a full-blown web server. It's not for doing a bunch of things. This is for getting two different devices to talk to each other, right?
Right, very specific.
And that's all it does. Now, there's some other stuff happening behind the scenes to give you an idea. If you recall, we've got this proto language here. Well, there's a compiler that actually compiles this into a bunch of Java classes. Now, what I've done is I've set up Maven to automatically call this compiler. And you can see what that looks like here. If we look over in Maven, here is a protocol buffers plugin, and this basically figures out what OS you are and what language you want, and it goes and compiles everything. So that's the Maven config. What it actually does is it generates, Maven, of course, will compile everything, and you'll have a single jar to work with. But you can also see the sources that were created by GRPC. So here are the various sources that GRPC created. As you can see, it's a considerable amount. Now, one of the things that I want you to notice is basically everything that we described in that over here seems to have a class over here, which is pretty much what you'd expect. And so they're creating classes. They're also creating the builders for you, and everything you need. Now, if you remember when we did this in Java before, we also had to create messages. Here they all are, right? And so, you know, each of these were all pure Java code, right? So here's a block message. It's Java code just to say that I've got a block. You know, you want to request a block? Hey, here's a hash asking for the block. You know, if you want transaction, here's one holding a transaction. All of this is really kind of boilerplate Java code. And you can see I have a whole lot of boilerplate Java code. Well, all that boilerplate stuff is now being generated for me because I only had to describe it here. And the best part about this boilerplate that's being generated for me in Java, this compiler can generate it for us in JavaScript, in Go, in C++, in Python, right?
Nice.
So that becomes really useful if you want to have multiple platforms talking to each other, especially if you have to maintain the code on each side.
So this one language can compile into any of those languages you mentioned.
That's correct.
Have you tried to do it to any other language or just Java?
I haven't tried to do it to any other language, but there's a whole lot of other people using this. So, you know, to give you an idea, this isn't just some, you know, random open source project. Google runs this for all their internal services.
Nice.
So there's a substantial amount of use of this code base. There's substantial activity. This is really robust stuff.
Seems to me like when I consider this kind of stuff compared to like AWS Lambda, and which would be better, or and then which applications would be more suited to one or the other. This seems almost better in some ways. Any thoughts on that?
Well, it's interesting because, if you think about it with Lambda, right, you write the Lambda function and then you have to configure the API gateway so that it can provide the HTTP REST side for your Lambda function. So in that way, it's similar in that, you describe a little bit of information and then AWS takes care of making the REST endpoint. But at the same token, it is REST and JSON, so it's still going to be slower than this is. So there's no reason why you can't do this and that. And in fact, there's even some people who've started doing this. There's now a community of where you can build plugins for the compiler, for the proto compiler. And so, for example, there's one plugin that actually you can put in comments in here, much like you would do in Java code, and it creates documentation for you. Another plugin that was interesting is one that actually will take all of this and will create a JSON REST HTTP 1 proxy for the protocol buffer HTTP 2. So you can write this and have best of both worlds. So any of the code that uses HTTP and protocol buffers goes fast, but it backwards supports all the old stuff.
Huh.
So some cool stuff.
Yeah.
But as you can see, we're really eliminating a lot of work here. We're basically pushing it onto the library, and we're just giving some declarative description of what we need, and then away we go.
Can you think of any immediate application for us beyond the blockchain stuff in what we're working on currently?
Well, I mean, certainly we could look at it from a standpoint of some of our APIs, making them more performant. So for example, having our controller talk to our backend, it currently does that with JSON and REST. And as you know, there's a number of devices that are constantly communicating, and there's overhead for every single one of those. So if we move that over to this approach, there'd be a considerable savings in performance.
Now, it's interesting because absolutely it seems like there would be, but we just did this work for porting to AWS Lambda, and now this looks like it might even be better, and perhaps not even that much work. It may not be on the critical path right now, but just as far as do you think how valuable do you think that work would be to maybe even skip over the Lambda AWS functions and just go straight to something like this?
Well, I think that it could be valuable over time. So, right now, we've got 100 or so devices that are hitting the back end on a regular basis. That's going to explode into 1,000.
Yeah, that's
really soon, right?
Yeah, exactly.
So when those numbers start getting bigger, any savings on overhead starts to really add up.
Right. Excellent. Okay.
Anybody else? Questions? You guys want to see any other code? I mean, I think this gave you the big overview here.
Have you committed this to the token GitHub?
Not yet. I am in the process of basically making a new version of the daemon. So I showed you some of the RPC calls are done, but not every single one. So there's a few more to do before I can completely switch over.
All right.
The other thing I was thinking about is from a organization standpoint, given that the way I have it right now is I have the protocol embedded in the same project and Maven configured to automatically compile that. I'm wondering if it makes sense to actually break that out into a separate project where you can compile from that same language into multiple stubs, not just Java, but the other language stubs, and run that as a kind of a separate project. I haven't really decided which way I like better yet, but that was something I was thinking about.
Okay. Yeah, that's interesting. This is pretty cool stuff. My mind is going in the direction of, how could we leverage this in the shorter term, but probably deserves some more thought.
Yeah, one of the other cool things is you can turn on TLS on all the communication as well. And you can do that with self-signed certificates or what have you. So if you want everything to be encrypted, that's, just a, configuration field.
Just a switch, right?
So that's really nice.
Mario, Carlos, Horace, we don't have Daniel on the call, and Melvin is missing too. But from the guys that are on the call, any comments or questions or observations?
Well, at least from my side, this is all new, right? I hadn't heard anything about protocol buffers, right? But yeah, like as Matt mentioned, sometimes serialization of objects through data standards like JSON on certain platforms, they may be a bit troublesome, like Java, right? Or they just have more of considerable, let's say, we have to code more in order for those things to work on certain platforms, right? Specifically in this case, Java. But this would actually ease up that troublesome, because one of the examples that I've seen this is that on the Lambda functions, for example, for the input and output on Java, we have to create like specific, let's say, for the POJOs or the standards of how we want to receive the data, right? And sometimes this may pile up. But yeah, it's something totally new for me, at least, and I'm gonna look a bit into that. Oh.
So Mario, with since Daniel's not here, do you want to sort of just give him a high level? I think we're going to have this video. Matt, are you going to be able to post the video?
Yeah, so this is all recorded and you can play it back later.
Excellent, excellent. Will you be able to post that link to Slack or?
Yeah, I will.
Fantastic. Because I'm going to get Daniel to have a look, since he just did the Java API, just to get his thoughts on that. Because if this is all fresh in everybody's mind, if it's pretty straightforward, it might be worth spending some cycles to get ahead of it. You've done a lot of work here to push it forward, and you know how it is when we put things aside for a while, it can get lost, right? So maybe we should take this opportunity if we have the bandwidth once Daniel has a look at it.
Okay, well, sounds good. Anybody else, or we all done?
Carlos, any thoughts, since you've been working on the client code and the Java API code as well? Any thoughts from you?
Really, this is a little bit new for me as well. I mean, I did have a little bit of experience straight out of college with writing like a small HTTP 1.1 server, nothing too big, but I hadn't even heard about gRPC before. I really like when you just kind of describe an object, and then whatever library or framework will do that jump for you of actually writing all of filling in the needed stuff. I was like that, and this was really interesting. I really liked the approach that these guys took.
It looks really powerful. Yeah. Great.
All right. Well, thanks for taking the time from all the things that you're busy working on just to see this and get some feedback. I'll continue along on this and at some point get it pushed up to Git.
Great. Thank you, Matt.
All right. Thanks, everybody.
See ya.
Thank you, Matt.